quite often we have a bunch of information, a bunch of data, and we manipulate them. So like you get one image and then you want to see who is this person. So this image contains lots of components, lots of pixels, or you receive a voice signal or music and then you want to see what tone is and so on. So transformation of a random vector is the first thing we want to learn about. So transformation of random vectors this is nothing more than what you have learned, just is a simple generalization. So suppose that you have k functions. So suppose that you have x1, x2, xn random variables. So basically this is a random vector. Okay, and then you give these inputs into a function, let's say g1, and then you get one random variable. So you get one random variable. If you give it to g2, you get random variable g2 and so on. So suppose that you have k functions like that. So then you will get k random variables. So we can define the first function of these n random variables. So you have n input, and you have n inputs here, and then you have k output. Usually it is hard to find a joint distribution of entries of z versus the joint distribution of entries of x if the number k and n are different. So if k is bigger than n, then the distribution, the joint distribution of z is certainly degenerate because you have generate no. So it's usually is degenerate, not always. Sometimes we have exceptions, but usually. Now if k is less than n, it is hard. So so what we do, we define some auxiliary random variables to make these to add to the k and then make it equal. So in that case, we may determine the moments or joint distribution of z in terms of the distribution of x. So the trick is that we use we add some auxiliary random variables, and then first the distribution or the joint density of the new set of random variables. So this is a portion which is z, and then we add some auxiliary. So in this example, I said, okay, I add the remaining n minus k. So if this is k plus 1, so I add n minus k functions. This is in general case n minus k function, but to make it simple, you take some of them and add it together. So what you see is that the size of this random vector is the same size of x, and the problem can become much easier. So we find the joint distribution of entries of z, and then from that joint distribution of y, so from f y of y, then we can find and eliminate some of the entries of y, which are these ones, and find the joint density of z. So this is the trick that most people they apply. So the first step is to find the density of y for the random vector y at y. And this step is to solve the following system of equation, because you have y1, which is this is a known value, and then you put the values of x. So you get k equations, and here you get n minus k equations. So in total you have n equations, n unknowns, and then you try to solve it. If there is no solution, PDF of this guy is 0. If you have one unique solution, or if you have multiple solutions. So if there is no solution, the PDF of y is 0. So this is obvious. And if you have a single unique solution, then the PDF of y is equal to the PDF of x. This x is the solution of this set of equation. So once you solve it, so this x shall be written in terms of, so the x is written in terms of y1, y2 to yn. So these x disappears. You put those solutions back, and the same thing in the Jacobian. And you can calculate the entries of the Jacobian, because you can, from this one, you can calculate partial derivatives with respect to x1, x2, etc. And those partial derivatives, you put it in the first row. You calculate the partial derivative of this one with respect to x1, x2, etc. You put it in the second row, etc. And then partial derivative of this one will become just non-zero on it. So these matrix, here you are going to have 0, and then you have an identity matrix, because here, you know, is simple. So then if there are several solutions, then we have to add the solution. So if you have several solutions, so you put a sum here over all possible solutions, and then you put the expressions of those solutions in those things.